Hello, Algebra 2 Geo students. New unit, new topic. Current unit is systems of equations. Hopefully you've seen some of this before. For sure you've seen these two variable systems before in Algebra 1, but I'm going to do this day to review it just to make sure that we're all on the same page. So it says, what is this and how is it different from what we've seen before? Well, hopefully you've seen it before. But the deal here is that we have a linear equation, which is the most common kind, the kind that we've probably seen a bunch before. We're going to have something like, there's many different types of linear equations, but the kind that we're going to be thinking about looks something like, let me get the pen the right way here, would be like x plus 7 equals 15 or something. Linear equation. There's just one x and it's raised to the first power. And this could be a more complicated one, but this is a pretty simple one. And the solution is a number, x equals 8, a single number. Solution is a number. Just a set of the solutions to this is just equal to one number. Systems of equations, though, have two variables and it always come in pairs of two. So it'd be like x plus y is 15 and x minus y is 1 or something. So usually there's an x and a y and there's always two equations because you can't solve it with just one. And the solution to this is something that looks like this, like 8, 7. And you see that the solution here, solution is a pair of numbers. Basically, for a linear equation, there's only one variable, so the answer is just one number. For a system, the solution is a pair of numbers. It's usually written like this, particularly if it's x and y. You write it like a coordinate pair, like x comma y. You could also write it like x equals 8, y equals 7 or something. These are kind of interchangeable. When we think about these things in graphs, we're going to want to use the coordinate pair because that's how we graph things, but you could always use this too. So that's one thing that's different. Like if you have a system of equations and your answer is x equals 4, it's not right. It can't be right because the system has a solution that has two different numbers. Okay. There's a couple ways to graph these things, or to solve these things, excuse me. Graphing, substitution, elimination. We're going to start with graphing. To me, it's the most intuitive, even though it is the least common. So basically, given these two, this is a system of equations. There's two variables, x and y, and there's two equations, so that makes it a system. And so we could graph this thing. We could graph these lines. This one has a y-intercept of +3 and a slope of -5/3. So it starts at 3 and it goes down 5 and over 3. Rise over run, yeah. So this first one's going to look like that. Something like this. Down 5 and over 3. Comme ça. Let's say that's the red one. And then the blue, I'll make this one the blue one, and that one has a y-intercept of -1 and a slope of -1/3. So we draw another line, which we'll make blue just to make it pretty. Starts at -1, that's the y-intercept, and it goes down 1 and over 3. So it goes through this point here, that point there. So down 1 and over 3. Should look something like this. And the solution to this system is the place where these things intersect. It's like kind of like you see that these things, these things meet right here. And that is the point 3, -2. 3, -2. And the claim here is that this point, 3, -2, is the solution to this system. This is the pair x and y that make both of these equations true. So we could just check just for fun. I'm going to plug in -2 for y and 3 for x and see what I get. So -2 equals maybe -5/3 times the x is 3 plus 3. So let's see, -2, is that equal to, let's see, -5/3 times 3, those 3's cancel out, and you get -5 plus 3, and that is true. -5 plus 3 is -2, so that one works. You try it again for the second one. Let me make this a little longer. Let's see, we have -1/3, so it's still the same x and y. The claim is that this pair of x and y here, this point, 3, -2, is the x and y that makes both of these equations true. So we'll just check the second one. The y is still -2. And we're like not sure, so I put a question mark. And then we got -1/3 multiplied by the x value, which was 3 minus 1. So -2. See, -1/3 times 3 is -1 minus 1, and that is -2, so it works. So that's how these work often. You'll see that, we'll see in a minute, that sometimes these systems have a single solution, like here, 3, -2. Sometimes they have no solution. And sometimes they have infinitely many solutions. And maybe you can guess a no solution situation would be where the lines never intersect, because where they intersect is where the solution is. So if I have a pair of lines like this that never intersect, there's no solution. And what that would look like on the graph is the lines would be parallel. They would have the same slope. So let's see if there's one of those coming up here. Looks like this one's going to work. So I'll draw these lines real quick. We get -x plus 3 is going to be a 3 and then a slope of -1. So that would look something like this. And this one's going to be -x minus 4. That one starts at -4 and also has a slope of -1. That's going to look something like this. And just for the sake of being complete, I will extend these lines to the edges of the graph, which is something you should do. And I get these two lines, and you can see these things are never going to intersect. They have the same slope. And so what that means for us is that this system has no solutions, meaning there is no pair of x and y that makes both of these equations true. That's what I mean when I say a solution. A solution to a system is a pair, x comma y, an x and a y value, which when plugged into both of these equations is going to make them both true. We saw back here that the point where x was -3 and y was, where x was 3 and y was -2, that works in both of these equations. Here, this parallel line situation indicates that there is no pair of x and y that makes both of these true. And when that happens, we would say the answer is simply no solution. The third possibility is this kind, y equals x plus 1 and -2x plus 2y equals 2. So I can graph this first line, y equals x plus 1. It's going to have a slope of 1 and go through 1. So it's going to look something like this. And it will go on to the edge of the graph, something like this. And there's your line. That's y equals x plus 1. That is, I'll make it blue, just so we have it identified as blue. And then to do the other one, I'm going to have to, like, it might be hard to graph this one from this form, so I'm going to have to solve it for y. That's normally the way that we do that. So let's say I'd add 2x to both sides and get 2y equals 2x plus 2. Then I would divide both sides by 2. And 2y divided by 2 is y. 2x divided by 2 is x, and 2 divided by 2 is 1, so I get x plus 1. That's the same as this one. So the red line is this one. And it's like the same as the other one. So if I tried to graph it, it would be like right on top of the other line. So it would look like, it'd be like right on top of it. And so, and this is kind of a weird concept, like where does the red line intersect the blue line? Well, it intersects it everywhere. Like every X value, any X value you choose, that any point you choose on the blue line, it's going to be on the red line because they're the same line. So when that happens, it means that every X and Y that you can plug into this one that works is also going to work here. It's got to, they're the same line. So when that happens, we say infinitely many solutions. I often abbreviate this as IMS in this unit because it's a lot of words to write. So whenever you have these two lines or these two equations and they're essentially the same equation, you get just a line right on top of itself. And that is the infinitely many solutions situation. That looks a little better. You'd think it would be purple, but apparently that's not how Smart Notebook works. But you can see the red and the blue line are right on top of each other. So that is systems by graphing. The other two methods I think you've probably seen before. Let me just fill this in. So now we know that the system can have three different types of answers. It can have a single answer. And by a single answer, I mean like a single set of X and Y, which make both equations true. A system like this is called consistent. Consistent, and it's called independent. The second one we saw was this one where there were no solutions. So it can have no, I'll call it an XY pair, maybe. I said a set up there. I'll call it a set. No set of X and Y, which make both equations true. And that's called inconsistent. Okay. And lastly, this one where they were right on top of each other, we have infinitely many solutions. We call that, so that would say infinitely many sets of X and Y, which make the equations true, which make both equations true. And that is called, let me rewrite that because that is terribly messy. That is called consistent and dependent. So one set of X and Y that make both equations true, that's called a consistent independent system. No set of X and Y which make both equations true, that's called inconsistent. And infinitely many sets which make them both true, that's called consistent dependent. We saw on our graphs that this means the lines intersect. If we're thinking about the graphs, this one means the lines never intersect. And this one means that the lines are the same. They're like right on top of each other. So that's the method one. I'll probably do both methods, both of the next methods in the next video, just to save us from making this video super duper long. So keep an eye out for it.